Thank you very much for inviting us to the Institute of Research Group. It's a pleasure to be here, and it always brings me a lot of good memories. And every time my wife is here, she wants to bring, this time she really wants to bring the grandchildren. I've been robbed by the Princeton and the Institute. And the first time I gave a talk at the Institute was in 1975 when I was in a member seminar. And I had Borel, Wade, Chandra, and Langlands in the room. And considering the luminaries were in the room now, I don't know if this will be my last time. So I hope it's not. Anyway, okay, I want to talk about some consequences of the local harmonic analysis and representation theory to global questions and vice versa. So I'm going to take F to be a local field. It could be periodic or real. And I want the G to be a connected deductive. I will specialize soon. And I would like that, as usual, I'm going to use the time of F, the SL2, SL2C, this is the first, so this is Freydoon loop. And then we finally have the G check, the complex group, so it's G check of C. And we have LG, which is G check times the wave group. All right, so we have these definitions, and then I want to just quickly review the local Langlands correspondence. Local Langlands correspondence, I think most of you know, but I'm just going to be very brief. They are homomorphisms, so local Langlands correspondence, they are homomorphisms from the wave group, Freydoon group, to LG, and they are under G-check conjugation. And then they are admissible, up to conjugacy, they give a finite set of representations of G of F, and that makes up a so-called L packet. So there's a finite set of L packets. Finite set of reps. We usually, if I call this phi, we usually denote it by pi of phi. And you can make these things, more solid by looking at the centralizer. So phi is the centralizer of the image of this thing, phi of prime inside G check. And then look at this and divide it out by its connected component and the center of G check, but the invariance of the center of G check. Now, this is called the component group. And the dual of this parameterizes this set. So the dual of these things, so if I look at this phi, the one all the irreducible representations of this finite group, this will parameterize in one correspondence with representations in the packet.
What's the gamma?
Gamma is the column. Now,
In terms of choices,
if you
train choices, it will keep the same structure of homogeneous spaces.
Yes. No. And let me see if I can fit anything here. Now, usually when this phi is bounded, but I use a different phi, I think. Phi is bounded corresponds to tempered representation. Phi is bounded, the elements in the packet are all tempered. tempered, you can look at them in terms of their matrix coefficients to be L2 plus epsilon, or you can look at them as sub representations of representation induced from the discrete series on the Levy subgroups. And there are in the construction of, usually in the construction of the local Langlands, there are some equalities of L functions which come in. Usually, when you look at even G equal to GLN, the first proof, which was given by Aristotle and Heniard, they made the correspondence unique in the sense that the L functions, Rankin Selberg L functions, agreed with the phi and phi prime, that's phi, and the same thing with the root numbers. So chi, this is the ideal character. And there are not many other cases when this matching happens. For example, for GLN, you can prove that if you look at these are Rankin-Selberg, these are ordinal functions attached to these representations. And then there are some cases, for example, for G equal to GLN. And for the representation, you can take a representation R of check, and you can look at you can just compose your S, phi, R, and then on the other side, there are choices of analytical functions. There is S here. I can take pi here, so pi use of that admissible GLMF. And I can look at L of S pi and then wedge square, exterior square, and it is Cogdell, PSNI, Cogdell, and my student side. We proved this, that they are equal. Of course, this was already done by Heniard, but we proved the root numbers. And then two of my students carried these to the twisted case. So if you take an arbitrary character, suppose I take a character eta, and then you look at the L of S, phi, chi, and then compose with some wedge squared. And in the other side, you can look at L, S, pi, and wedge squared. So these are proved also. Also, this equality is also proved. And the L functions on the right are the ones that is in this list of L functions that I mean, following Langlands developed. Now, these are the twisted L functions. You cannot prove them by that. There you will use classical groups. Here you have to go to G-spin groups. You have to go to the covering groups to produce that. So these are, and also the same for epsilon. Of course, this is always easy. The epsilon part is much harder. You have to prove the stability. The student who did this is she, and my other student, Daniel Shankman, did outside. So, of course, I mean, the new approaches may make these things as secondary as not, I mean, you could use these to make them, to really pin down the local Langlands, or you can look at the stability of the characters and make that to pin down the local Langlands. But since we have the local Langlands for GNN, we can do it in here. And pi, this pi here comes from, pi is in there. Make it a phi. All right. Now, what I'm going to do is I'm going to state the resulting representation theory that Castleman and I proved some time ago, and use that for two reasons. First, to get something about the Ramanujan and also get something about these the intertwining operators and the arithmetic in Eisenstein cohomology, and that Harder and Raghuram have been working on. So let me start trying to state what I really want to start with now. So let GB, GB as above, cause split. Assume G is a quasi split group. I mean, unitary, orthogonal, I mean, special orthogonal, symplectic, all of those guys. And let me take P, the parabolic subgroup in here. Of course, we always fix it for L containing a unique maximal torus, and then you will assume that, well, okay, let's assume P contains this, and of course, L contains T. Then this will be uniquely give you the Levy decomposition. I will assume that P is proper. So P is inside G, but it's not equal to it. So P is a proper parabolic subgroup. And let R and let's let R joint action of L group of M on the L of N. This is the Lie algebra of L. This is the type of representation which appear in the Langlands constant term of the Eisenstein series as developed by Langlands. And so I'll take this representation, I'll denote it all of it. I mean, without not worrying about S or 2S or something, I'll just take the whole adjoint action and denote it by R. Now, then let phi be a tempered representation of M of F. And so it's tempered irreducible, of course. Representation of M of F. And let me take pi of phi. Like it.
Parameter for M.
Didn't I say tempered parameter?
You took a representation.
Tempered parameter. Sorry. This will be denoted by sigma. Sigma will be in here. And this is the L packet of phi, and phi, I'm sorry, phi is a parameter. And it's tempered. It's a parameter and it's tempered. Okay. And then I'll take sigma, an irreducible representation inside this packet. And then there is a conjecture, by a conjecture in my 1990 annals paper. There exists a representation, there exists a sigma, which is also generic, which is also generic. Okay. Bring it down. Now, if you fix your character chi, then this representation is unique. And there are many cases of this. It's proven now for classical groups by Arthur, I mean, Ginsberg, Alice, and our work. I mean, Kim, Shahidi, Piatetsky, Shapiro, and Kambial. If you put these three words together, you can prove this thing both locally and globally. That a temporal L packet has a generic representation. And it is in Arthur's book. Now, let me state the theorem of Castleman and myself, or for position if you want. Okay. I'm going to make the following assumption. Assume, let me write this. This is in unscientific here, and this is actually 90. We showed that assume, I'm gonna, that this theorem doesn't depend on this assumption, but let me make this assumption. Okay? And is the following, that in that setting, I have this parameter phi, I have a representation sigma inside that, which I'm assuming is generic, so I can use the other L function. Suppose I know the Artin L function, which is this L of S and phi, then composed, remember that's R. That in that representation, adjoint action is R. And I think I explained it. So where did I put that? Yeah, it's the adjoint action is R. And then I'm going to take this thing and compose it with this representation R. I have my G, I have this particular parabolic L, I mean P equal to Mn, and I have R, I compose it with phi, R was this action. And I'll assume this is equal to the one which comes out from the method. So that's just going to be R of S sigma, and let me just write R. That's the method. And this is from this method. Okay, so this is the assumption that these two L functions are equal. And as I said, we can prove it in many cases when these particular representations show up. Now, then the following is true. Let me consider, assume sigma is a quasi-temperate, irreducible generic. I mean, I'll assume irreducible temperate, irreducible generic representation of M of F. I'm assuming that it satisfies this property. And I'm assuming that I'm putting it quasi-split in a way that the resulting induced representation gives me a standard module. That's why I make it to be in the positive chamber. Assume that it's a positive chamber. Then I'll compute the, let me put I of sigma, this representation, P of F, G of F, sigma, and so on. Let me take this now, normalize operator and anything. And sigma is the one, of course, sigma is in pi of F, I'm sorry, pi of phi. Then this representation is irreducible, then this representation is irreducible. If and only if this Artin function evaluated at 1, Artin function evaluated at 1, or phi inverse is 0. It's not 0. And it is reducible when it is equal. So this gives you all the reducibility points for these induced representations. Okay. And of course, what we prove is we prove about this, but I'm making this assumption. The nice thing about working with this thing is that this has parameters in it. And I can control the behavior. If the parameter is bounded, I can get results from that. Okay, so in that side, I can get this. Now, as I said, this irreducibility has applications in the work of Harder and Laguren. And also has consequences vis-a-vis Ramanujan's conjecture. I'll try to talk about those. Now, I'm gonna now introduce let me use this mode that I have here. I'm going to introduce author packets, so author parameters. This is quite general, but just for the sake of what, if I get time, what I'll do at the end is that I'll take Gn to be as O2n plus 1, P2n.
Can I ask a quick question?
Yes.
So suppose you didn't make that assumption that the ordinal function is LS R phi is LS sigma R, then would this, you replace this?
Then it will be replaced with something about this guy.
So it's say L1 sigma R
Yes, right.
is not a pole. So that,
Yeah, this will be replaced. I mean, this will be in here. The thing in here is that now I can benefit from phi. If phi is bounded, it will tell me something. Okay, it will tell me something. So I transferred it to here. Otherwise, we can just use this guy. This is what you use.
yes.
Okay, now RSO to N. Alpha, I mean, for a quasi split, alpha is a square class. And then if you look at the auto parameter is a map of the F, that's set to Z. This is the ring. That's set to C, and this is the order. Okay, so I have these things in here. And missing an H. Order is set to C. And it's a map to LG. L2. Now, the restriction to W, the image of the part restricted to W of must be basically semi-simple. It must be bounded. These two are, these two will be, these two are going to be representations. So then I can write psi as sum of things like this. Phi I tensor SMI and SMI. Now SMI is a MI dimensional representation of SL2C. SNI is an I dimension. These are unique of that given dimension, and this is a homomorphism of WF. And this has to be bounded, semi-simple and bounded. Bounded, and these are supposed, these homomorphisms supposed to be analytic, so they are really these representations. So an auto parameter can be written as a finite sum of such things. Okay, finite sum of such things. And then there is a very important homomorphism that you can get out of this. In fact, an L parameter that you can get out of this. You can define phi sub psi to be defined as x, w, x, and then defined at the, so this is a Langlands parameter. So it has to be defined in WF times, which means SL2C, that W prime F. So it's going to be phi sub F W X, and that's going to be psi W X, and then in here, W 1/2, 0, W minus 1. And this will give you an L parameter. This is a homomorphism into LG, and it is just restricted to the radial lingual. Okay, so this and the point is that psi 0.25 psi is an injection. Is an injection, and then of course I can take that packet. Phi of 5 psi, this is L packet. This is to be contained in what we call pi of psi. This is called an Arthur packet. Now, an Arthur packet is a collection of representations, reducible admissible representations. These are local Arthur packets. L packets are not, they are disjoint local Arthur packets or not. So that's a problem. Local Arthur packets or not. Arthur packets consist of local components of the global Arthur packet. So the things which parameterize the automorphic, the L2 spectrum. Okay. So these are called the representation called of Arthur type. Local representation, if it sits in, it becomes a component of one of these things. These Arthur representations which are in here are supposed to be unitary. They should stay away from, they should satisfy in some sense Ramanujan if you are with GLN. And that would mean that there should be no complementary series among these guys. So these are elements inside the Arthur packet. Now, these things, although I mentioned it for these groups, but you can define these things completely generally. Whether now the whole point of what Arthur did, Arthur took these parameters, he defined them in terms of information on GLN and parameterized the global representations in terms of data on GLN. And there are, if you read the book, you will see that this gives you choices. These things will really parameterize the whole automorphic spectrum. All right, now, all right, let me get to the connection with the connection of this theorem, and in terms of this equality, let me get something out of this, and that would be about Ramanujan. So let me start with the following theorem. This is in Kyoto Journal. It was not out of duality or whatever. I think it's 1911 or something. I'm 2011. That would be very bad. 2011, and this is, I see, but suppose A is valid. Suppose A is valid. Now, assume that this Langlands packet, this pi of 5 psi has a generic element in it. Has a generic element. Okay, if this is so, then this thing would be bound. Then psi would be bound. So basically, that will say that pi of 5 psi will be tempered. So if you have an R2 packet in which there is a generic representation, then it's tempered. So it's really a Langlands packet in that sense. Okay, and when I talked about this thing and we discussed it with Wang Liu and my other colleagues, this conjecture that there is this enhanced conjecture. It says that I can write it in the A packets are tempered, A packets, outer packets tempered, i.e. have bounded parameter if and only if they contain a generic representation. They contain generic representation. Okay, so this follows from using the boundedness of phi when you have a tempered parameter. Now, so you immediately see that. So what we really need is this equality, and this is not true in general anyway. You have to do it in cases, but they are surely true if the field F is real or complex. So proof these are equal, or if representation sigmas are ramified. So these equalities hold, and automorphic forms are at almost all the places unramified. So then we can say something about them that these, if you have a generic representation, then it's all tempered at almost all the places. So this basically says if you want something about Ramanujan, stay away from against Ramanujan, which will happen for a group except GLN, stay away from generics. Because generics will parameterize tempered packets. Okay, so let me put this in some. There's a conjecture of Clausel which help us do this. In conjecture is proof for classical groups, so it's a let me now this is a I called it conjecture literally. This is due to Clausel Arthur also thinks it is true, and I think for the classical books, we know now they are proofs by Wang and two of our students, and also proof by Arthur for this. This is Clozel. You notice everything that I have here is about this particular L packet. It's not about the A packet. Okay, so that's what we have to take care of. Clozel says that the assumed size of global Arthur parameter. Assume it's a global Arthur parameter, and then it will define for each V, it will define a local Arthur parameter besides V, and then of course that's right. I assume by V, and then of course what Clozel says that this is a Cospedal representation. Representation. So we are over a global field now, and then let's look at then of course we have a global packet by psi attached to this psi guy, and then we take almost all V is pi V. Pi V is spherical, which of course this is trivial. This is spherical and belongs to that Langlands packet. Phi of psi. So this means that whatever I proved about this parameter applies now to the local component of these. And you clearly can see that if you have a generic, then I can say on a theorem here of the Ramanujan. Then we'll look at what happens after this. I mean, put the generics away, then what can we do? Of course, now nice thing about generic ones are that every tempered packet has one, and then we can develop a theory of a function even for the other ones, for non-generic ones. But with this in our hand, let me write it. This is again Q2. And then I'll tell you about the new results. Assume conjecture A. Assume conjecture A. Okay. Let this be let I equal to tensor product B plus 1 be a locally generic, meaning it has a local. Let's go on. Representation. What's your group here? I mean, if these things true is any quasi-split group. If these assumptions are any quasi-split group, Cospedal representation, and of G of A, now A K is number free. G of A K. Then pi V is tempered, then pi V is tempered. It's tempered. At almost all. So being locally generic will allow you to conclude that pi is tempered, because at almost all places things are spherical, we can use this Clozel's. So this means that do not worry about the generic ones. They will be tempered. So worry about non-generic ones. And that's where we can think of wavefront sets and other representations in Arthur packets. Now we have to look at the genuine Arthur packets. Right. So let me I want to talk about wavefronts.
I have a question. It's Peter.
Oh, hi.
When you assume generic, you're saying locally, what are you assuming about pi? It's locally generic at, how do you check this?
If it is locally generic and if you have this conjecture A, then you will be able to
but locally generic at one place, then you can conclude it. What's happening there?
I'm saying, I'm really looking at a globally generic, even if you want, but they are local.
So it's globally generic in the sense of globally having a Whittaker function?
Yes, but I mean, you can also assume everything is local because it comes from these authors.
I understand that almost all places,
yes.
I'm saying if I have a pi and I have a place at which it's locally generic, is that enough?
No, for me, it's not enough. It has to be locally generic for almost all the places.
Okay, so
if it is a spherical and generic, then it is enough in that one.
Okay.
But you want to get tempered everywhere. I mean, you could have tempered in one place, but not all the places.
In another, right. So I'm just trying to understand how I check this condition. I mean, so I either have to check it at all but finitely many places.
Yes.
Okay. And you probably can say how many places? I mean, in practice.
Yes.
Okay.
Basically work with the spherical ones.
Okay.
At the moment, there are some good results by Chebotarov and Harris, Michael Harris, over function fields. They have results of this kind that you have this representation and it is nice in a few places, then it satisfies Ramanujan.
Yeah, okay, that's basically my question. Yeah. Okay, thanks.
All right, so now let me talk about wavefront sets. Now G again, connected reductive. And let's assume that there is this results of Harishchandra. Now, if you take F p-adic, then you have a local character expansion, pi irreducible admissible.
You mentioned the work of Harris and his co-author. In that case, in the function field, do they work with general G?
Quasi split, of course, and no, there are some exceptions. It has to be, cannot be an F4, cannot be that. They have some exceptions.
But the point is, they're not relying on Arthur's description. So
no, this is over function fields that they are.
Right. So in other words, I just again your assumption A, which you say is more or less a theorem, will be for classical groups, and
I mean it's proved.
These.
I mean that Ramanujan's conjecture is proved for the classical groups.
Yes, so I'm just trying to distinguish that in the function field we don't have to make that restriction.
No, it's more general, but of course there are some restrictions in function field too that is not general. I mean, cause split. It's some. Okay. There are some exceptions.
All right, but the point is that if you're a skeptic of these kind of conjectures for exceptional groups,
I'm not of these conjectures.
Yeah, I know you aren't, but suppose somebody is, then they would feel a little more comfortable given that in the function field these things work out.
Yes, right, exactly. Yeah, okay. But I mean, I asked Harris, they are not thinking about order, but not exactly in the format of order, because I mean, over function fields, we don't really have really theory of order packets and things like that. But they are thinking about that general ideas.
Okay.
And so I have an irreducible admissible representation of G of F. Then there is just a neighborhood. This is well known. This is all. There is just a neighborhood U of 1 such that if I take a function F in CC infinity of U, so U is inside G of F. Then I can write an expansion for its trace. So I can compute its characters, so trace of pi of F, which is the integral of the trace of the integral of f of x, pi of x dx for g of f. This can be given as the character expansion. This can be written as a sum over O runs in the nilpotent orbit. So O is all the nilpotent orbits, And then to them, this is really like the way the wavefronts are. Then in here, you can have constants. And then if you want to have Fourier mu of f, and of course, mu is just the mu of f is just mu of f. Just the integral of the Fourier. I mean, all its things. The mu O of u over u, of course, you can do it. This would be over the whole O. For every orbit O, I have a measure d mu O, and I integrate f tilde. Now, f tilde is just f tilde is f exponential. All right, then this would be something on the Lie algebra. Then I take this thing, and that is the Fourier transform. This thing. Now, this is the Fourier, this is the character expansion of Harishchandra. And how? And it's just written like this. And the question is that, what are these guys? What are these? These are explicit, but what are these guys? And even more importantly, are they zero or are they not zero? The orbits of the largest dimension, when C of pi is non-zero, they are called wavefront sets. So wavefront set are all O such that CO of pi is non-zero. And one of the problems that we have to deal with is to see in the Arthur packets, what are the wavefront sets? And that's a very hard question. And so this is a project that Boeing, Liu, and I are doing. And sort of extend what I've been talking about here, because when you have a generic representation, wavefront sets consist of the regular orbits. The largest orbits are the wavefront sets for generic representation. And with this thing, this means that the wavefront set for anything else, which is not tempered or is not generic, has to be smaller. Okay, so the question is, what is that? Now, there is a conjecture of Georgian, which tells us what it should be, but it's not really the full generalization of my conjecture that every tempered packet has a generic representation. You like to have that every packet has some particular kind of wavefront set, but at least in the case of Arthur packets, he formulates a conjecture for us. So let me at least, I can just formulate it. I don't know if I get to any details. So we have psi Arthur parameter. The question is, what are the wavefront sets? What are the wavefront sets? Pi psi the Arthur packet. How can we predict them? I mean, in the tempered case, we predicted that there's a generic one, and generic one is the wavefront set. It's the highest, correspond to the regular, the largest dimension. And the question is that for a general Arthur parameter, what is this? And this is basically for the classical groups. Although many of these things can be taught generally. Now, let me give you a couple of information. Let me put, remember we had that Arthur parameter, I haven't erased it. Maybe I did. There were three elements. There was a phi I, Sn I, and Sn I. And phi I is, so I'll take phi I, assume the dimension, this is the dimension of phi I, this is mi, so this I would denote by ai, and I put bi to be just ni. I rename it, and then we can come up with a partition. The partition is, I may assume b1 is bigger than b2, bigger than br. Okay. And I will assume, so then I can come up with a partition. This is in the Young diagram of partition. I can write b1 to a1, br to ar. So this is a partition of n is just going to be sum of ai, bi. And of course, since it goes to it, it's a partition of, in the case of, for example, sp2n, this would be partition of 2n plus 1, because the L group of sp2n is 2n plus 1. And so we have that this gives me a partition, and a partition points to an important orbit through the Jordan decomposition. And of course, you have for GLN, and then if you look at the classical group, it sits inside GLN, and if you have a symplectic group, the odd ones should appear with even multiplicity, and if you're in the orthogonal group, the odd ones, even ones have to appear with even multiplicity. So you know exactly which one of these really lie inside one of these classical groups. And let me just define duality. I did it. All right. Now, let me remember I had GM, which was this either SP2n, SO2n plus 1 or SO2n alpha. So GN is one of these guys. Then I put G equal to Lie algebra of GN and G check, Lie algebra of GN check. They are in duality, of course. GN check, sure you have SP, it goes to SO and so on. And then there is a so-called Barbash-Vaughan duality. Barbash-Vaughan duality. What it does, it starts from the permutation on GN check and brings it to a permutation on GN. So it starts with an nilpotent orbit on GN check, I'll explain, and goes to an nilpotent orbit on GN check. So this is supposed to tell us what happens to wavefronts. So let me do this. Now, this is one nice place to see this, is this paper of Archer, 2003. How is this defined? It's pretty easy to define it. Okay. Eta of these two. Apply to a permutation. So let me apply to a permutation P. P is permutations of G check. This is it. Give it a name. You can put the complex numbers there. So Ada will take a permutation on GN check. So SO, for example, SO2n, and takes it to a permutation on SO2n or SO2n1, bring it to SP2n, and this will be Ada of this thing will be something in the permutations of GN. So this allows you to pick up at least nilpotent orbits going from the L group to the group. You can pick up nilpotent orbits through this. And I'm going to explain what this is at least.
When you speak of nilpotent orbit, you are geometric or over the local field?
Or over local fields.
Because it's not just a partition you need that. For SL2, for instance.
Oh, you need also some character or something. So, but I mean, I'm talking about partition. I'm talking about if you are in SP2n, I'm talking about the partitions of SO partitions of 2n plus 1. That's what I mean.
But that's not enough to give a conjugacy class of unipotents. For SL2, you have
Yeah, I know. No, but
one of non-trivial one.
let's do it over algebraic closure. So that do it over algebraic closure. That would satisfy you. So I'm going from SO to N. I'm taking partitions of here, and I'm going to the partition of 2N, which will be 2N is the speed 2N is the group which has the L group SO2N plus 1. So I'm going from that to there, and this is going to give me a partition. So it is defined as follows. Let me quickly tell you. So it is if G check is different from G, in our case, so this would be SO2N plus 1 or SP, then eta of this partition P is going to be equal to, I'm denoting it P transpose plus minus and then a collapse. Okay. Now, what is P transpose is you have the Young diagram, you transpose that matrix, and plus minus is that if you have a partition ER, plus means that you get E1 plus 1 and then E1 or 1 minus 1 and you go to the end. And minus 1 means you take E1 to the R1 all the way BR to the A1 all the way to A1 minus 1, then BR minus 1. So this is the partition that you can find this way. And all you have to do is transpose it, apply psi or minus to it, depending on the situation, and then collapse it to G. Now that means find the nilpotent orbit which is below it of lower dimension, or in the closure relation. Okay, that's what collapsing is. And this is when they are different. If they are the same, which is just a case of SO2, and then you're going to get that. This thing is just going to be called P transpose. Now, this is how you go from the L group to the group, and then the Young's conjecture basically tells you what should be the wavefront set for elements in an order packet. So let me quickly say that, and I'll stop. I'm not going to go to any. By the way, those in SL2 are really like two regular orbits. Yeah, there is, of course, like that. There will be things like that. They would not be unique. Even there will be things that there are examples when they are nilpotent orbits which are not even related to each other, even over algebraic closure. So those there will be even for generic ones. There are two. You're right in that sense that there will be two orbits. Even for orthogonal.
I'm confused that one group is over the local field, the other group is over C.
This is basically, just look at them as partitions. Look at them as partitions of 2n and partition 2n plus 1 and partitions of 2n. That's okay?
Except it's coarser than looking at unipotent orbits.
Except what?
It is coarser than looking at unipotent orbit. Maybe it's geometric unipotent orbit, but
I think, I don't know how to answer that question, but it's surely, I mean, if you, I don't know if these are geometric.
does it mean over the algebraic closure of the local field you were on?
Yes, over algebraic closure, we are fine. But what I'm saying is that even over algebraic closure, they could be non-related nilpotent orbits. This was a surprise. This is very new. For I think, I don't know, U7 or something they have found. Something like that. Now let me just finish. At least I'll tell you what is the Young's conjecture. So pi. And then let me denote by this wavefront set. Set of pi. And then what? And then of course, let me take a order parameter.
Or what is the context?
This is classical groups. This is classical use. Yeah, there is nothing in general.
So, and when you speak of wavefront set, it is which those coefficient
Those level coefficients are non-zero, the largest non-zero coefficients. An outer packet, and this is an outer parameter. It is local, of course, and we are just dealing with the local field at the moment. Now, let me take, so the Young's conjecture. Young makes the following conjecture. First of all, it says that for any partition P, which is not related, not related to this thing, to this Wahlberg-Vogel transfer. Not related means that it's not in the closure of its orbit, of the orbit. Okay, so then if they are not related, then you cannot, then the wavefront set, then, and if you take pi psi, the outer packet, pi of psi, then this thing, then this P, if you have a P, which is not related to this packet, then this will not appear in the wavefront of this thing. Then P is not in PMO. So for any element, any pi in the outer packet attached to psi, if you have a P which is not related to that guy, then that P cannot be in the wavefront. The second one, I mean, this is because of this non-related stuff. The second one, I can just put it here, that suppose P is bigger than, so they are related. Suppose P is bigger than eta of P of psi, then when pi is in the outer packet, pi is in the outer packet, then P is not in the wavefront. Meaning that this is the largest possible wavefront. And finally, the third one says there exists a representation. So you achieve this. So the third is there exists a representation. Pi. Wavefront set on this. Contains this eta. Eta is in there. Okay, this is the conjecture. We can prove it in certain cases, and I think it's not too late to try to explain the results that we have proved. We can do certain cases of it, and this is really trying to move on beyond the generic case. You have to worry about these wavefront sets, and you have to worry about the behavior of the character expansion. And I think it's a hard problem. We are also thinking of the generalization of my conjecture to arbitrary Langlands parameter, rather than just artifacts. Okay, sorry, thank you.
Can you tell what generic means in terms of those coefficients?
I mean, in the case of generic, I mean, if the representation is generic, that's CO of pi for all the regular O's are non-zero. And then, of course, depends on what kind of generic model pi has. If the generic model pi has, I mean, if you're SL2, for example, there will be two different generic models, and there will be two different O's. One of them would be non-zero. Okay, so they are, and we know that they're equal to 1 because it also gives the dimension, and these go back to Langlands and Walsh version.
Yeah, actually, I had a question about some of that relating how this relates to Vogler-Rashford. If I remember right, the CO pi is the dimension of some kind of degenerate Whittaker model.
Right. I mean, they try to produce the largest Whittaker, I mean, the biggest collection of Whittaker models for all kind of characters. I mean, they're generalizing the generic case, and this relates to that well. I mean, you can really connect these things to those models.
In characteristic P, can one sometimes use something else and the exponential?
You mean for the COs?
Yes, for for the structure of the character, I am very ignorant. So for GLN, you can use 1 plus x to make the Lie algebra looking like GLN, but is it good or not?
I don't know. I don't know how to answer that. I have never thought about for the characteristic positive case. You know, Chandra never thought about characteristic positive.
Any questions from Zoom? Yeah, yes, Peter. Go ahead.
No, I'm just, thanks for the lecture.
Thank you, my pleasure. Thanks for inviting us.
Question. So you said conjecture A, this Clausel, this is known for classical groups.
Yes, yeah.
And so for classical groups, you have Ramanujan for almost.
That the generic ones, yeah, are Ramanujan. Yeah.
What is the story for, we just chatted for about even for GL2 over a number field?
I mean, the thing is that
What is the
these things have to do with validity of, Ramanujan for GLN. You see, when you have then you have Shalaka proves this, that all the class forms of GLN are generic.
yes.
Okay. Now see, this basically assumes that the GLN, the parameters that these are parameters on the classical groups, they go to become parameters on GLN. And being bounded in that sense means being tempered. And that should be equivalent to being Ramanujan. For GLN, this says nothing. I mean, the Ramanujan itself is an arithmetic question. If you have all the transfers, then you have Ramanujan. It's a hard question. I mean, Peter asked some, density conjectures. He was telling me, and that may give us some better approximations of the conjecture.
Yeah, but the way Arthur's work plus the fundamental lemma reduce the description of Ramanujan to that of Galen in classical groups. That's why I was asking the question over the function field, where you're not relying on his work, where if these things bear out in exceptional groups, it gives us confidence in the other for.
I think their cases includes exceptional groups.
Right, which I think is very good sign, good point about it. Yeah,
that's right. Yeah, no, I think they use fact about representation theory quite a bit.
Let me ask you an old question. You remember in the old days, Piasecki Shapiro used to talk about cap representations.
Yes.
And there were conjectures there about generic as replacements. This is before all the more recent works. So did those turn out to be correct and now proved, or were some of those actually wrong?
I think some of them are wrong. I don't think they are an issue now. They are not being really looked at seriously. Cap representations are non-tempered. They are representation which look like Eisenstein.
Right, but there were attempts to try to fix up the naive Ramanujan in that way and there was is one consequence of your Kyoto work that if you don't obey Ramanujan, then you will not obey it at all but finitely many places. Is that true?
Yes, yeah. If you know it is generic at almost all the places, then it is tempered at almost all.
Okay. Yeah. So that's already clean.
You cannot have tempered. You can have tempered in one place and not tempered anywhere else.
Yeah. Okay. Perfect.
There was examples like that. You have discrete series at Archimedean, and everywhere else is a disaster. They're not tempered.
Mm-hmm.
If there are no other questions, let's start Freydoon again. Thank you.